Hello everyone, and welcome to this session on industry transformation with hybrid cloud. My name is Prashant, and I'm the CTO for IBM's Asia Pacific region. In today's session, we will be talking about the telecom industry, and I'll be taking you through some very interesting transformation work that IBM and Red Hat are doing together at one of our key clients in the region. As we work on hybrid cloud transformation with clients in different industry verticals, we recognize that industry context is extremely critical to achieve high-value transformation outcomes with hybrid cloud. In the case of telco, which we will be covering today, you will see that there are significant benefits from cloud transformation in terms of revenue, CapEx, and OpEx. Additionally, hybrid cloud also enables our clients to create digital ecosystems and, in some cases, manage regulatory compliance. This requires deep, opinionated industry patterns for the hybrid cloud transformation. In today's session, I'll be taking a real client example from the telecom industry where we are actively executing some of these transformation patterns. Specifically, I will explain how we are achieving end-to-end cloud lifecycle management and what we call zero-touch build and operations for complex network workloads. Let's start with some industry context. One of the key challenges telcos face today is the commoditization of their key offering, which is connectivity. While OTT players and digital platforms have clearly benefited from the pervasive connectivity provided by telcos, the telcos themselves have not been able to offset the revenue decline through new revenue streams. At the same time, as data growth skyrockets, the CapEx and OpEx productivity of the telcos has not kept pace. Now, the idea of using cloud and network virtualization technology to help address CapEx efficiency as well as achieve greater automation in operations is not new to telcos. However, most telcos have deployed their network clouds in the form of vertically integrated appliances that support virtualization inside. This means that they are unable to achieve CapEx efficiencies and economies of scale across these silos. At the same time, they are unable to achieve operational automation and standardization across these different islands of operations. So the transformation work we are doing with telcos is essentially to address these challenges. The key idea is to establish a common open cloud across all of the telcos' workloads, which will enable efficiencies and scale at the infrastructure layer, and at the same time achieving standardization and automation at the operations layer. While this addresses the CapEx and OpEx concerns for the telco, this also provides a common service composition environment on top of which the telco and their ecosystem partners can create value-added services to offset their revenue decline. To better understand the nature of the transformation involved, let's take a look at this visual. In the case of vertically integrated clouds that are shown on the left, each of the cloud silos has its own infrastructure, its own virtual infrastructure manager or cloud, its own set of software, and its own control plane for orchestration and management. Since none of these layers is standardized, each of these silos have to be typically managed by different teams of operations. This eliminates the possibility of standardizing across either the infrastructure or the operations layers. At the same time, it makes it extremely difficult to achieve service composability for value-added services on top of these silos. The target state we want to achieve is shown on the right of this picture. As you can see, in this case, we have established a common horizontal cloud that supports all of the telco's workloads in a unified manner. This allows us to achieve significant economies of scale and standardization at the infrastructure layer, while at the same time allowing the operational efficiency of a common cloud. The diverse workloads of a telco are supported as software on top of this cloud, much like we support different ISVs and enterprise applications in a typical enterprise cloud environment. Sitting above this layer is the control plane of this cloud, which basically has all the orchestration and management capability for the cloud. This layer handles all the day 0 through day 2 operations for this cloud and is the source of significant operational efficiency for the telco. Finally, all of this standardization allows us to create a service composition layer at the top, which enables creation of new revenue generating value added services on top of a common cloud. However, as all practitioners know, it's not enough to just envision this nice target state. The gap between technology and outcome is often wider than the Grand Canyon. It involves a complex transformation for us to get to the end state. To help you appreciate the complexity of this transformation, let's look at the workload and ecosystem diversity that we are dealing with in case of a telco. As you can see here, to support core edge and far edge workloads on a common cloud, you have to take into account the significantly different performance requirements that these workloads place on the cloud. Core workloads, as an example, are focused much more on extracting the maximum amount of capacity and performance from commodity hardware. Whereas on the edge, we need much more flexibility to compose different kinds of services together. At the same time, it's possible to have much more resource pooling and sharing on the edge. And lastly, at the far edge, where we are dealing with the radio network, the workloads typically require low latency and reliability, and we often have to combine real-time operating system capabilities along with the core cloud. You will also see that the diversity of the ecosystem in each of these categories of workloads is quite high. Having a common cloud essentially means that we should be able to support day 0 through day 2 integrations required with all of these ecosystem partners across the spectrum of workloads. To support these diverse workloads and ecosystems on a common cloud, we need to standardize and automate aggressively and establish common lifecycle management across these workloads. This figure illustrates the approach that we take to establish this common lifecycle. The starting point is a catalog of workloads that can be deployed on the common cloud. Here, you would expect the telco to keep adding new core, edge, and far edge workloads over time from their different partners. At the next step, a network planner or designer takes control and configures and sizes the workload based on domain-specific knowledge about those workloads. A standardized view of the workload demand then needs to be packed and placed into the cloud. Remember, a telco will typically have many distributed data centers where different kinds of workloads are deployed. As a result, we need a standard mechanism for performing admission control and placement under various kinds of performance and affinity constraints. This step leads to what is called a low-level design or an LLD for the workload deployment on the cloud. This may involve creating new cloud instances or adding workloads to an existing instance. At this step, we achieve standardization by having multiple cloud-specific or NFVI-specific models for the deployment. These models provide a consistent way to automate the deployment of these clouds. The deployment of the network applications, which is the VNFs and CNFs, on top of this cloud then follows standard declarative software-defined principles. Finally, a completely software-defined model of the application, the infrastructure, and their configuration can be handed over to day 2 operations. Now, with this context, let's now look at the actual execution of this transformation at one of our key clients in the APAC region, which is Airtel. Let's look at the actual implementation of this lifecycle at one of our key clients. The starting point is a catalog of workloads that can be deployed on the cloud. This includes core, edge, and far edge workloads. In a telco, typically there will be many cloud data center locations spread across the country, as shown in the map on the right. In this particular case, we are either instantiating a new cloud on bare metal or adding new workloads to an existing cloud instance. So let's go ahead and select a VEPC workload, which is a virtual enhanced packet core workload, to be deployed at a new location. This means that we have to first deploy the cloud itself and then add workload onto it. This is typically where a network designer or planner takes control. They will configure and size the workload and choose what compute and networking infrastructure they'd like to run it on. All of this is driven by a software defined model of the workload. For example, the model captures the components of the workload, which in this case are the SP gateway and the MME. The SP gateway is sized based on traffic in Gbps, whereas the MME sizing is based on subscriber attach units. Once this step is done, we have a workload demand that needs to be packed and placed on the available DC resources. This step is a constraint optimization problem, where we have capacity constraints and workload affinity constraints, much like a bin packing problem. An algorithm then computes a server, fabric, and a rack plan. Based on the constraints, we see here that we need 20 servers of different profiles, and that these servers are to be deployed in different roles. Some of these are for the OpenStack cloud itself, such as the undercloud, the controllers, the Ceph nodes, etc., whereas others are for the application workload. Similarly, the rack plan follows constraints on power and space and provides us a rack placement for our planned servers. And finally, the fabric plan tells us the server port mapping, switching, and cabling that we will need. To help you appreciate why all of this needs to be done programmatically, consider how this planning is manually done by telco engineers and planners today. This is an Excel sheet containing what is called the low-level design, or the LLD, of the network cloud. All the tabs at the bottom represent different aspects of the planning that we've shown so far. Now consider the next level of detail behind each of these 4 planned racks as an example. Each of these sheets captures the server to switch mapping, the VLANs, and the network interface bonding details on servers based on the application workloads placed at each of these servers. You can see why this is such a bad idea to do this manually. Not only is there loss of productivity and room for plenty of error, but imagine what happens when you pass this back to operations. It's a nightmare to ensure consistency between what's planned and what's built. And imagine how we would handle FCAPs in this way of working. Going back to our life cycle, we now generate the LLD automatically. The network planner now provides a set of key IP planning inputs that will be used to generate the LLD. Each of the planning sheets we saw before are now generated automatically without any room for error. The last crucial step is to take this plan and convert this into an automated cloud deployment. In our case, the cloud is OpenStack, which uses a multitude of YAML files to automate its deployment using Red Hat Director. We auto-generate these YAML files dynamically from our LLD. This completes the final step in our fully automated cloud build, from catalog to planning to deployment. Now that the cloud is built, we can commit it to our data center inventory. This updates the data center state and ensures that subsequent workload deployments go through the correct admission control. We use Netbox as our data center information model here. You can see here that this represents the client's data centers, and in this case the model is initially empty. Once we commit the LLD to the DCIM, we can go back to our original catalog and select the DC to see whether that state is duly reflected. In this case, we see the 2 racks duly populated in the DCIM model. And we see all the server configuration duly reflected in these racks. We also find all the granular details corresponding to each of the bonds and the various network interfaces, VLANs, etc. that are configured on each of the nodes. With this, we have effectively closed the loop and reconciled the newly built cloud with the overall state of all of the telco's cloud sites. Now with our cloud ready to go, we can shift our attention to the application or the VNF or CNF deployment on the cloud. We will illustrate this using two applications, a Cisco EPC service and an AltioStar vRAN service. These applications are described typically using Tosca or similar formats, and we often have to work with either vendor-specific heat templates or vendor-specific VNF managers to do the deployment. Here we will switch to IBM's orchestration solution, which does this work. We will first start with the Cisco EPC service. We will use three views to capture the deployment of the application on the cloud. The first is from the IBM orchestration solution that uses an intent-based execution engine. This models all of the application's resource dependencies and dynamically computes the correct sequence of bringing the application up through those resources. The intent engine in turn calls out to the vendor-specific VNF manager or heat templates. In this case, this is Cisco's ESC or Elastic Services Controller. The ESC ultimately provisions the VMs and the logical networks on OpenStack, thus completing the deployment of the application. The last mile of this execution can be seen in the Horizon dashboard of OpenStack. To see that the approach generalizes, we repeat the same process but this time with a different vendor and a different application, which is AltioStar vRAN. Once again, the IBM orchestrator does the top-level control and sequencing and ultimately calls out to vendor-specific functions to do the last-mile provisioning on OpenStack for virtual machines and networks. Like before, we see the application coming up successfully, in this particular case showing successful pings between key components. So what kind of measurable business impact is this work really creating at our client? For starters, the time to deploy a new cloud site end-to-end has gone down from 71 days to 2 days. The reason for this aggressive optimization is all the standardization and automation that we did along the way. On the CapEx front, remember the improvement comes from two sources. First is from going from PNFs to VNFs, which is physical network functions to virtualized network functions. And the second is further efficiency that we get by establishing a common horizontal cloud. The collective impact of these improvements is close to 80%. As we deploy these workloads into day 2 operations, the expected OpEx improvement from the managed services teams and the operations teams of the telco is close to 50%. And finally, we are looking at significant revenue uplift from edge services that the telco will now be able to deploy on a common cloud at the edge. In conclusion, I would like to reaffirm some of the points that we've made throughout this session. Firstly, to achieve high business impact through hybrid cloud transformation, we need industry depth and expertise. And to illustrate this point specifically, we've discussed one opinionated transformation blueprint for telecom. It's also critical to point out that it is key to have client commitment to these transformations. These are not just technology transformations. There is significant interlock required with business and operations because these transformations involve new ways of working. And finally, IBM and Red Hat will continue to establish joint strategic references such as the one that I took you through, not only in telco but in other industries such as banking. I hope you found the session useful and it has given you a first-hand view into both the complexity as well as the high impact of some of the hybrid cloud transformations we are doing in key industries with our clients. With that, I'll close this session and I thank you for your time.